Okay, welcome back to the third part of our mini lecture course. Right, a brief reminder of what we did last time. I tried to explain you what random errors are, where they come from, and how you can perhaps model them. And I discussed measurement errors, which might come from a scale you read. Reading error, measurement error, which could be an error which is propagated through many little errors in your experiment. These errors tend to accumulate and give you some large error. Counting error, which can be calculated directly. And sampling error, which comes from taking a sample from a much larger population. And in a population, you have some unknown parameters, like the mean. In sample, you calculate sample mean. And this is an estimator of a sample population. So statistical estimator, that was another important part of this lecture, is a sample attribute used to estimate a population parameter. And there's lots of them, like mean, variance, it could be correlation. And I discussed a few simple estimators, standard deviation, which is calculated usually with n-1 here, and standard error of the mean, which comes from the sampling distribution of the mean. Now, I really appreciate your feedback that you left in your forms. There are still some of them circulating around. And some of you pointed out that the standard error wasn't explained maybe very well, and that was one of the most difficult concepts in the last lecture. So let me just devote one slide and a couple of minutes to standard error of the mean again. I'll try to explain it maybe from a slightly different angle. So what you really want to consider here in order to understand where it comes from and how it's calculated is a difference between a hypothetical experiment, this Gedanken experiment, where you can, for example, draw 10,000 samples of 5 mice and then measure them, weigh them, and find the mean weight of each sample. And then you can build a distribution of sample means. And it is plotted here. So if you do repeated experiments, you find the mean in every experiment is slightly different. And if these means, they wobble around and they change a lot from experiment to experiment, that means that you can't measure your mean very exactly. It's rather uncertain. And this distribution of means will be rather wide. If your means, on the other hand, are very close to each other, every time you measure precisely, or very similar number, that means we can measure it quite precisely, quite accurately, and the distribution of the means will be quite narrow. So the width of this distribution, the standard deviation of this distribution, is a good measure of uncertainty of the mean. However, you can't do this. This is a hypothetical situation. You can't measure this distribution. You can't do hundreds of thousands of experiments. What you have is just one real experiment where you measure 5 mice and you have 5 numbers. And from these 5 numbers, you measure standard error, and it's plotted here. Now, for the sampling distribution, we know from theory that this the width of this distribution is sigma, which is the population standard deviation, divided by the square root of the sample size. And this is a common trick in statistics. When you do something derived in terms of population parameters, unknown variables, you just replace them with known estimators, and you get something which can be useful. So you replace this sigma with the standard deviation from just one sample, and you get standard error. So this standard error is 1.7, while the true uncertainty of the mean is 2.2. So this is only an approximation of the true uncertainty. And as you can see, from experiment to experiment, it will be different, sometimes smaller, sometimes larger. This is basically, this formula here is our best guess on how uncertain the mean is. Now, that's standard error of the mean, which tells you how wide this sampling distribution is. And it is an estimate of uncertainty of the mean. But actually, we can do better than that. We can introduce something which is called a confidence interval. I'm sure most of you are familiar with this, so I will try to explain it in details. Let's go back to our population and sample. So again, a sample mean m is a statistical estimator of the true mean mu. So we can ask a question, how good is this m? How good is this estimator? And we can put, for example, standard error on this. But we can try to do better, and we can think this way. Let's build a confidence interval, which will be a certain range from m lower to m upper around our measured m, where we think the true mean is with certain confidence. So we have certain confidence, for example, 95% of confidence that the true mean is within this region. So we can express this in probabilistic terms. And this can be done for any population parameter, not only for the mean. You can do it for median, standard deviation, correlation, proportion, whatever you want. And I will show you today and in a week time, I will show you a few of these, how to calculate them. First, we have to understand properly what is this confidence that I mentioned. So just let us focus on a certain number. Let's consider 95% confidence intervals. These are probably most commonly used in biology. So we have this interval from ml to mu. First of all, this does not, I repeat, does not mean that there is a 95% probability of finding the true mean in this interval. The true mean, the true population mean, is just a number. It's not a random variable, so we cannot assign a probability to it. It's just there. We don't know it, but it's somewhere there. So what it really is, you have to understand this, again, in terms of repeated experiments. So if you were to repeat your experiments many times, for example, 100 times, many times, this is the experiment number from 1 to 100, and if you measure mean and confidence interval every time, that would mean that in 95% of cases, the true mean would be within this confidence interval. And this is sample mean. This is the 95% confidence interval. And the population true mean is indicated by this red line in the middle. So in most cases, in 95 cases, or percent of cases, the true mean is within this interval. In 5% of cases, it will be outside. That's your probabilistic statement. The only problem is when you do this, you have no idea which case it is. So you say only, okay, there is a 95% of cases where true mean is within our interval. But one particular measurement, you have no idea. If you calculate your mean and a confidence interval of this, you cannot be sure that the true mean is within it. It's only a probabilistic statement. Now, why 95%? Or alternatively, why p-value of 5%? It's commonly used. Well, it dates back to a textbook published by Fisher, Ronald Fisher, in 1925, where he stated that 95% confidence interval was convenient as it resulted in one false indication in 20 trials. That means that 1 in 20 experiments will give you the wrong answer. And he thought it was convenient. And he published also tables of probabilities, various probabilities distribution, and one particular column in these tables was for 5% or 95%, depending which side you look at it. And this book, this particular book, had become one of the most influential books or textbooks in statistics in the 20th century. Basically, everybody read it, everybody started from this point. Fisher was founder of modern statistics. So basically it stayed like this, and it's more customary now to use it. It's just tradition. But there is nothing special about 95% or confidence or p-value of 5%. You can use any value you want as long as you are consistent and you explain why you prefer this. Ronald Fisher, you've seen him before. I showed you this picture last time. As I said, probably the most influential statistician of the 20th century. He was also an evolutionary biologist. Interesting story about him. He went to Harrow School and then to study at Cambridge. And at Harrow, Arthur Vassal, who was the schoolmaster, and someone asked him one day, could you name me 10 best, most outstanding pupils you ever taught? And his answer was, well, 10 would be rather difficult. I would divide all those I had taught into 2 groups, one containing a single outstanding boy, Ronald Fisher, the other all the rest. That's the assessment. So statistics was strong with him, even in his young days. He was an outlier, okay? He was a bit of a strange man. He didn't like admin people for some reason. He said, an administrator, not the highest form of human life. That's a quote. But he was a genius, so we can call him eccentric for this. Yes, we won't hold it against him. Now, sampling distribution. So to understand confidence intervals, we have to start with sampling distribution and understand it better. You have seen it before. So I'm going to do another Gedanken experiment. So if you consider an unknown population we wish to characterize, and draw lots of samples of given size. This size is quite important. You set a size and you draw lots of samples. And for each sample, you calculate an estimator, for example, sample mean, and you build a distribution. So you have seen this distribution of sample means, which width is the standard error of the mean. But as I mentioned, you can do it for any parameter. This is sampling distribution of the median. It's a little bit wider, as you can see. So it's calculated from exactly the same set of samples. I simulated 1 million samples from this population, normal population. This is the sampling distribution of the standard deviation. It's a bit asymmetric. There is a tail here. This is mean deviation I mentioned last time. So all of these and many others, they are sampling distributions. They describe how a given parameter or attribute of a sample, how it behaves. Let's focus on sampling distribution of the mean. I will spend most of today's lecture on this. So this is a simulated distribution. Fewer points. There is only 100,000 samples, so you can see it's a little bit jagged, but yeah, it's still a distribution. So this distribution, this curve, represents all of the samples. So what we can try to do now is keep the region inside corresponding to a required confidence, for example, 95%. Because this distribution is, well, it doesn't have to be symmetric, but you want a symmetric situation where this desired probability is right in the middle. So what you do, you reject 2.5% on the left-hand side, 2.5% on the right-hand side, and what is left here, this is 95% of samples. So this is an interval that contains 95% of sort of a central samples after rejecting extremes. And this gives us a confidence interval for our estimator, and this is the 95%. Okay? Obviously, you can't do this in reality. You can't have an experiment with 500,000 mice. No ethics committee would agree to this. Not to mention all the local cats trying to get to your lab. So instead of using this unknown distribution, you can do some mathematical tricks and convert it into something known, a known probability distribution, and then you can calculate your probabilities or intervals, okay? So for a sample, you can find estimators like mean, standard deviation. N is something you usually set to a given number. Now, let us calculate this particular statistic. It's called T, and you must have seen something similar before. It's mean minus population mean divided by the standard error. It basically tells you how many standard errors you are from the true mean, how bad your result is. And it's a number which will be centered at 0, sometimes will be positive or negative. Now, this is only a mathematical trick. You can't find actual value of T because you don't know this. You don't know population mean. However, we'll come back, reverse this, and find some constraints on the mean by this. So, but before we get there, let's continue our Gedanken experiment and create a sampling distribution of T. So it's a sampling distribution. So what you do, you take every sample from this distribution, and instead of plotting M or finding distribution of M, you calculate T for every sample and build distribution of T's. And it looks this way. And this distribution has some very interesting properties. It's known, and you can probably guess what's the name of this distribution, because it's a distribution of statistic T. How is it called? not t-test, but t-distribution, yes? Students t-distribution. It's known, so these calculations finding 95%, rejecting 2.5 on each side is now possible. Right, so this is the t-distribution, students t-distribution. I didn't describe it when I went through all probability distributions. I really don't want to go too deep into this. Just quickly show you a few of them. So it is sort of a standardized distribution. So it's centered at 0 and its standard deviation is 1. You can shift it, but in a form we use it, it's always centered at 0. So there is only one parameter left, which is number of degrees of freedom, and it's related to our sample size. So for this statistics, it's sampling distribution, it is students t-distribution with n-1 degrees of freedom, and depending on number of degrees of freedom, it looks slightly different. At the limit of a very large sample, the t-distribution looks like Gaussian distribution. That's true for many other distributions. So this black line, it's actually Gaussian, it's normal distribution. But when your sample size is smaller, a smaller number of degrees of freedom, it looks slightly different, and you see it's got wider, longer tails. That's why this t-statistics behaves differently for different sample size. Now, students t-distribution. Why is it called students t-distribution? Well, it was developed and first presented by William Gosset, who was a brewer and a statistician. He worked at Guinness Brewery. And at the time when he was there, he was a statistician. He calculated things to improve basically working of entire brewery. And at the time he was there, someone from the brewery published a paper, a scientific paper, where they revealed some trade secrets of Guinness. And Guinness got very upset about this, and they decided that, okay, from now on, you cannot publish any papers. All employees are banned from publishing any papers. Whether it's trade secret or not, it doesn't matter. You can't publish anything. So it's, it's reversed to what we have here. It's publish and perish. So he published as a student. That was his pseudonym. And he published a few papers. And then he worked with Fisher and developed t-statistics in its current form, as we know it. It was called Z, well, in his original paper. He worked with experimental data a lot. He was a good theorist, but mostly worked very closely with data, so perhaps he was a father of all bioinformaticians. That's the original paper. He published it in 1908, and the confidence interval of the mean, he coded the probable error of the mean. This is the machine he used to process his data. Apparently, they had only one at Guinness Brewery, and he had to fight for it just to get access to this machine if he wanted to do some calculations. All you can do is just add and multiply numbers with this. Okay, let's go back to our t-statistics. So, as I said, if you do this calculation, do this transformation, this t-statistic has a known sampling distribution, which is a student's distribution with n- degrees of freedom. This is the analytical form of a student's distribution. And using tables of t-distribution or using statistical packages, you can calculate these probabilities. Specifically, for given probability like 95% or this tail probability of 2.5%, you can find the so-called critical value. Usually it's denoted as T star. I'm sure you have seen it before. If you wondered what it was, well, that it is. It cuts off required probability or confidence within t-distribution for a given sample size. So this is for the given number of degrees of freedom. So from this, we can find that the confidence interval in t-space is from minus t star to plus t star. It's minus t star and plus t star because this distribution is symmetric with respect to 0. So all you need is to find just one number here. The other one is its negative value. Okay, but this doesn't give us anything on the mean yet. So what we do now, we get back to our mean. Right, we have transformation, we have t-statistics, and we know that confidence interval is this, from minus t star to plus t star. Now, we can solve this equation for mu, for the population mean, which is this one. It's sample mean plus t times standard error. And now, because t we know the confidence interval on t. T is between minus t star and plus t star. So from this, we can find the limits on the population mean. Mind you, these are not limits on the sample mean. So if you calculate confidence interval, it's on the population mean. And the lower limit is this minus t star times SE, and the upper limit is m plus t star times SE, or you can just write it m plus minus t star times SE. So you can see this is the formulation of our confidence interval. You can write that confidence interval, CI, is a scaled standard error. It's a standard error multiplied by a certain constant, by a certain value, which is found from probability tables for the given sample. Okay. Right. Right. So just remember that it is a scaled error. Now let's do a little example, which I hope will make it easier to understand. Consider a sample of 7 mice, and we measure body weight, and these are these 7 numbers. So what I did for you, I made your life easier, and I calculated mean, standard deviation, and standard error. And now I ask you to find 95% confidence interval for the mean. So remember, the confidence interval size is standard error scaled by this t star. And you can find it from this table. This is probability here that you request, and this is number of degrees of freedom. It's actually a very simple calculation, and you must have done it before, unless you use only statistical packages for this, but looking at probability tables is sometimes useful. Okay, I give you 1-2 minutes. Please find for me 95% confidence interval. You might need a calculator, a phone, for example, a smartphone. Okay, any results? What's the size of a confidence interval? Anyone? Not yet. Okay, let's start with how much? 3.2. 3.2. Any other suggestions? 4.8. 4.8, okay. That sounds like an auction. Is anyone going to give more? Okay. Now, first of all, what's the critical value, t star? I just remind you, this is from this distribution, so you need to look at probability, sorry, the t corresponding to this tail. Where do you find it in this table? What's the value we are looking for? 8? 1895. Why 1895? Where did you find it? 0057. 005. Which column do we need to use? Second. You see, one tail is 0.05, 2 tails is 0.10. One tail, what we want is 2.5%, yes? Because we want to reject 5% of both sides. So we are looking for something that 2 tails are 5% and 1 tail is 2.5. Which column is it? This is third column. And which number in this column? How many degrees of freedom? 6, because there are 7, exactly. So we are looking here. 2.447, that's the scaling factor. So we take our standard error and multiply it by this, 2.447, and the number is actually 4.14 or so. So it's between these two suggestions. Okay? You need a sample size, you need required probability. These tables are printed in various formats, so sometimes it might be confusing what's here. You have to read very carefully the description of a table. Then you can find your critical value. So this is our scaling factor. So standard error is scaled by this number, and that's what we get. And the result is 22 plus minus 4 grams in terms of 95% standard errors. Some of you might be tempted to write it exactly as I did, 22.16 plus minus 4.14, which is wrong. There are too many figures here. Some of these figures are not significant. I will come back to this in 2 weeks' time. I will explain you how to calculate significant figures and how to quote these numbers. Right. Let's have a look at the standard error and confidence interval in more details. This is a sample consisting of, I think, 8 points. 1, 2, 3, 4, 5, 6, 7, 8. This is the mean plus minus standard error. This is the mean plus minus, that's basically entire 95% confidence interval. So as you can see, this confidence interval is bigger than the standard error because it's multiplied by this scaling factor. So the first question you might ask, how many standard errors are in a confidence interval? And basically the answer is here. This column tells you how many depending on the size of the sample. Okay? But you can look at this from a different point of view. This is 95% confidence interval. You can easily imagine calculating confidence interval for different probability. So if instead of 95% you take 50, presumably it will be smaller. If you take 99, it will be larger. So you can tune this probability to find a confidence interval which is the same size as the standard error. And then you can say, you can ask what confidence is in the standard error. Okay, so you can, by comparing these two things, you can ask these two questions. So the first one is quite simple. Right, as I told you before, confidence interval is a scaled standard error, and I expanded this equation. It's a very simple equation. Ci is T star times Se. But I expanded this to explicitly write down that this T star depends on confidence interval or required probability. I call it gamma here. So this, in our previous case, this gamma was 95%. And it depends on the sample size. This is number of degrees of freedom n minus 1. So these are these two things it depends on. And I asked you how we can find how T star depends on the sample size. So basically, how many standard errors are in the 95% confidence interval, because you multiply standard error by this function. And this is what it looks like. Now, you notice two things I want you to remember from this. First of all, when your sample is large, somewhere here, this is the sample size. It starts from 2 and goes up to 30. When your sample is large, you have about 2 standard errors in this confidence interval. At infinity, it goes to 1.96. But it's roughly about 2. And you can see this in this figure. This is standard error, this is 95% confidence interval. It's about twice. However, when your sample is small, this goes up dramatically, especially for the sample size of 2. For the sample size of 2, it's about 13. And this is bad, which means if you have only 2 data points, if you have only 2 replicates, and you calculate, let's say, standard error on this, and this is whatever, it's this size. This standard error, well, you don't know what confidence it has got, but if you convert it into 95% confidence interval, it will be 13 times larger, which means if you have only 2 replicates, there is basically no confidence in the result. You need more. You need more replicates. You want to bring it down here. And even 3 replicates, you drop from 13 to about 4. So the size of the confidence interval decreases very dramatically. Now, what is the confidence of the standard error? This is the opposite question. It's plotted here. So again, when sample is large, it's about 68%. This is this 1 sigma in Gaussian distribution. And this is because T distribution for large sample looks like Gaussian distribution. However, for smaller samples, this confidence is smaller. When you have only 2 data points, the confidence of the standard error is about 50%. What worries me more about standard errors is that this confidence is different for every different number of points. So if you have, for example, 2 samples, one of them consists of 3 points, another consists of 8 points, and you plot them in a graph with standard errors, the sample with 3 points will have confidence of about 50, maybe 7%, and 8 points will be somewhere here. It will be over 60%. So from probabilistic point of view, you will be comparing different things, which are not they are not compatible to each other, really. So that's why standard errors are not the best way of representing error of the mean. The best way is confidence intervals, because regardless of the sample size, they will have the same probabilistic meaning. So I encourage you to use confidence intervals wherever it's possible. That's yet another comparison. This is sample size of 8. This is sample size of 100. So sample is shown here. And I show, well, standard deviation, standard error, and the 95% confidence interval. As I mentioned before, standard deviation describes the spread of a sample, so it's roughly the same regardless of the sample size. It will go, it can be a little bit smaller or a little bit larger. It will vary. It's not very, accurate, but it's roughly the same. While these two types of errors, they represent error of the mean, and they get smaller and smaller as your sample gets larger. And also you can see that the standard error is, confidence interval is about twice the size of a standard error. This is true for the 95% of confidence interval. Okay, one more example exercise. Nothing to do calculations, but just to think about it for a moment. So imagine an experiment where a reporter measures transcriptional activity of a gene. So you get some numbers from this. And let's say it's a complicated experiment, so it takes quite a while to prepare your samples. So on day one, you or your student prepared 3 biological replicates because it was in the afternoon. And on the next day, the student managed to prepare 5 biological replicates. And this is the same experiment, but done on day 1 and then on day 2. You must be familiar with this. And results, well, these are results from the first day. These are results from the second day. And I calculated for you 95% confidence intervals for these two things. Now, what can you tell me about these results? And what else could you possibly do with this data? Is anything worrying here for you if you look at these numbers? It is supposed to be the same experiment, continuation of the same experiment, but on the next day. Look at these numbers. What's wrong with them? They are not overlapping. These two error bars are huge. They are 95% confidence intervals. This is from 0.56 to 0.84. This is from 0.86 to 0.94. They do not overlap. So if you saw data like this from the same experiment repeated the next day, what would you conclude about it as a biologist? Something has changed. Something has changed from day 1 to day 2. Might be easy to identify, might not be. But normally that was my question, what else could you do with this data? You could pull them together because we are doing the same experiment, and you can say, okay, we have 3 and 5, we have 8 replicates in total. But because we know that they are not the same, well, if you pull them together, this is the 95% confidence interval, theoretically, but probably it doesn't have very good practical meaning because something has changed. If you do a simple t-test between these two samples, you will get a p-value of 0.03. That tells you that something significantly changed between the 2 days. And I remember talking to some of you about experiments done this way where something had changed from one day to another, and you were confused. You didn't know what to do. Well, presumably you have to do it again. That's unfortunate. But yeah, you have to look at your data, and you have to look at confidence intervals. And before you combine all your data together, make sure these are true replicates. Because if there is a systematic shift between some parts of data, then what you get at the end, this confidence interval, would be rubbish, basically. So be careful. Right, at the end, one more thing I wanted to show you today. It's the confidence interval of the median. Now, I have seen in some biological papers, well, people use median quite often, especially if you want to avoid outliers. You don't want them to affect your result. You might calculate median instead of the mean. But people seem to be confused about uncertainty of the median. And I have seen in some papers there was a median quoted, and next to this there was standard error of the mean, because the person who did the calculations had no idea what to do with this mean. And it turns out that you can calculate strictly confidence interval of the median. And if you quote median, you can quote its error as well. It's actually quite simple. So first, I will show you sort of a theoretical background, where it comes from, and then show you a practical way of calculating this. So consider a sample of n numbers, x1, x2, up to xn. and let's call the population median theta. We don't know this. However, we know one thing. By the definition of the median divides population into two equal groups of the same size. So if you take one point, data point, and ask, what's the probability of this point to be on the left of the median? It's 50%. What's the probability of this to be on the right? It's also 50%. So mathematically, you can write it like this. For any xi, probability of xi being less than the median is half, and being greater than the median is half. So if you do this experiment and draw one point after another and decide whether it's on the left or on the right, it actually corresponds to a similar experiment I discussed before. It's like tossing a coin, and you say, okay, if it is heads, it's less than the median. If it is tails, it's greater than the median if you do a random draw. And this, as you know, leads to a binomial distribution. And it's this way. So imagine that you now order your sample, and this is quite important in this calculation. So you have to sort it from the smallest to the largest number, and I denote it as brackets. So x brackets 1 is the smallest number in the entire sample, and x brackets n is the largest sample, and all the other points are here. Now, the probability, so you remember if you toss a coin many times, the binomial probability distribution was built in such way that we asked, what is the probability of having k heads out of n coins? You remember this? It was 2 weeks ago. So you can do the same here. You can ask, what's the probability of finding this value, this population mean, between k points and the remaining n minus k points in the middle? That will be the same corresponding probability and leads to binomial distribution, which is plotted in this diagram. For example, this is the position in the sorted sample. So this is not actual value, it's just a rank. This is the smallest number, this is the largest number, and there are 18 numbers here. So the probability that the true median is somewhere between 9th and 10th number is this one, about 17%. And probability that the median is between 5th and 6th point is much lower. It's maybe 3 or 4%. Now, I say probability of true median being between 2 points. This is not very accurate, and I mentioned this before. What I really mean is that because this true median, it's not a random variable, it's just a number. So it's it's basically, if you repeat this experiment many times, then in maybe 17% or so of experiments, the true median will be somewhere here. So you build this distribution, and what you can do next is cut off required probabilities on the left, on the right, just as before, and this is what is left. So if this is 2.5%, if this is 2.5%, then the confidence interval on the median is somewhere between 5th and 14th point in the sorted sample. This is theoretical thing. Unfortunately, because this distribution is discrete, you can't cut off easily with this, the exact amount of probability, because you might say, I want 2.5% here, but it will be, at this point, will be maybe 4%, at this point will be 1, so you jump. It's the discrete distribution. So you need to interpolate, and there is a clever way of doing this. It's a little bit complicated mathematically, but presumably if you use some good statistical package, it will do it for you. So you can do this calculation. And now I'll show you a practical way of doing this. It's actually very simple. You can do it on a piece of paper and perhaps with a pocket calculator. It's an approximation, but it gives fairly good result. So take our sample, and you sort it first. So you have to order it from the smallest to the largest point. And then you find your limits on, not on actual data points, but on these indices or ranks. And not sure if you are familiar with these symbols. This thing with little things at the bottom is called floor. So it's the largest integer number which is smaller than your number. Floor of 3.4 would be 3. 3.4, 3.5, 3.1, any number, it will give you 3. It's just integer part. This one is called ceiling. So it's the integer that is larger than a given number. And ceiling of 3.4 would be 4. It's quite simple. So you find these two limits, and the other one is just n minus L. And then from this, you can calculate standard error of the median. which is actual value x at this point, this point minus this point divided by 2, and then find confidence intervals exactly the same way you do for the standard error of the mean. You find statistics t, critical value t, but you have now u minus L minus 1 degrees of freedom, and multiply it by the standard error, and these are your intervals on the mean. I'm pretty sure it's not very easy to understand, so I will show you an example. Okay. Consider this sample, 9 mice this time, and body weights. There are 9 numbers. So first thing, if you want to find median and its interval, you have to order your sample, sort it from the smallest to the largest, and this is the index. So this is the first, second, third, up to the 9th point. Now, median, obviously by definition, is right in the middle. This is your median. So median is 20.1 grams. That's easy to find. Now we use this equation to find L, the lower index. So n divided by 2, n is 9, n divided by 2 would be 4.5, and the floor of 4.5 is 4. This one, if you calculate it, is very simple, is 1.5. Ceiling of 1.5 is 2. 4 minus 2, this is 2. And the upper index is n minus this one. So it's 9 minus 2. It's 7. So these are your limiting indices. And these 2 points will give you the size of the standard error. And the standard error is the number at this index minus the number at this index divided by 2. So standard error is basically half of the interval between these 2 points. And if you calculate it, you do these calculations, it's 1.4 grams. This is standard error of the mean. When you look into tables of t-distribution, you remember that now you have different number of degrees of freedom. It's u minus L minus 1, 7 minus 2 minus 1. You have only 4 degrees of freedom. And you find critical t multiplied by standard error, and this is the confidence interval you can obtain. Okay? This is this result presented graphically. This is the same sample example I showed you in the previous slide. This is the mean, and it's 95% confidence interval. This is the approximation I showed you, and the 95% confidence interval. And that would be a result from the strict method that requires interpolation, and it's a little bit more complicated. You see this is asymmetric. It just reflects that asymmetry in the sample. So these, of course, these 2 things are not exactly the same, but the difference between these 2 errors is really not that big. For bigger samples, they will look much more similar. So this is the method described by very simple equations, and this is the result. Okay, thanks a lot. Please leave your feedback forms here, and see you in a week.